Good morning. Today we'll continue the about the dissolving material reductions over the lecture. So we have discussed so far first type, second type, and third type. Today we'll discuss about third type of dissolving material reductions. Reduction of that is reduction with metal and alcohol. Okay. So we know already we have discussed earlier that dissolving material reactions can be classified to three main types of reactions. First one is reduction with metal and liquid ammonia. This is we have discussed in the earlier. This is bar reductions is one example. And second type is reduction with metal and acid. That is we have discussed also in the last class about Clemenson reduction. So in the third type today we'll discuss this third type is reduction with metal and alcohols. So these methods, metal and alcohol, used for the uh, reduction of carbonic compounds to alcohols. So carbonic compounds here, compounds are reduced. Compounds are reduced to corresponding the corresponding alcohols alcohols by metal with metal and alcohol. Say, for example, say aldehydes. Okay, aldehydes are reduced by metal and alcohol to primary alcohol. Similarly, that ketones, these carbon groups ketones, are reduced by metal alcohol to the secondary alcohol. Okay, so this is a secondary alcohol. Okay, so this reduction with metal and alcohol is used mostly for reduction of carbonic compounds to the corresponding alcohol. That means aldehydes are reduced to primary alcohols and ketones are reduced to secondary alcohol. These are primary alcohols and this is secondary alcohols. Okay. So there metals here. Metals can be used either in the free state, either in free state, or you can say or in solution. In solution, say in liquid ammonia. In solution, say in presence of liquid ammonia. Okay. So along with the alcohol. So metals can be used either in free state or in solution with liquid ammonia. So metals can be also used you can be used in say amalgam system like sodium amalgam, like then zinc amalgam and magnesium amalgam. Now I'll give some examples about reduction with metal and alcohol. I'll give some examples. Okay, some examples on reduction of reduction with metal and alcohol. Reduction with metal and alcohol. So in this case, I'll give some examples. So for examples, this 6H13 is cyclohexane, ketone, hydroxyl. These ketones with sodium in the presence of ethanol, and this reflux with xylene or toluene reflux. Okay, and carbon compound is reduced to secondary alcohol, CHOH and CH3. Okay, this is one example. And another example we can have, say like this. This is another example. So let us have ketone here, and this is aromatic system here. Here also same case, we can use amalgam system, sodium mercury, and this even acetic acid also can be used in the ethanol, alcohol, acetic acid, like this for hydrolysis. This will give, this can convert it to, so here this is just to this secondary alcohols. Okay, so I'm giving one example here. Many examples many examples about this also here. But another one example that is very good. One example is so this metal can be used in presence of isopropyl alcohol. So I will give the examples metal in presence of isopropyl alcohol. So we have submembrane CLS submembrane carbon group at metals like sodium in benzene and isopropyl alcohol. Isopropyl alcohol is like this. Two CSOs. Then here the reflux in the either in the reflux in toluene. Okay, reflux in presence of toluene. Okay. So here carboning group is this carboning group is reduced to this alcohol. Okay, secondary alcohols. So it's one example. For one example, we're using isopropyl alcohol. Many examples are here. Then I will get the mechanism of the reactions. Mechanism of the reaction for the reaction like see this one. This carbon group CH3. So you can have this. You can write this way. This carbon group and this hydrogen and this is methyl group. Okay, this is methyl group. So this one. So this can be mechanism. This can be reduced fast with sodium. Sodium will give the electron pass here. Then they go this one way. So we get first step is formation of anion radicals or anion radical here, and first formation of anion radicals, hydrogen, this is methyl group. Okay, so fast formation. This one again you can write this way in presence of proton donor as a presence of ethanol alcohol. So you get this one. The product will be first step is you can have this way. Okay, so you have OH here because of proton, then hydrogen here and CH3. Then this again repeat the sequence with a metal again. So another electron is passed to this. So we got this one. Another electron is passed. So we got anion here. So from radical converted to anion by another electron passed from the metal electron. Then we have CH3 here, methyl group. Then again this one again with proton donor. This anion can be converted into the final product is alcohol. Okay, this is converted to in presence of alcohol is proton donor. Then this converted to the proton. This okay, we got a second alcohol like that. So this is the product, final product. So what I say, ketones are converted to secondary alcohols by metal and alcohol. So this is about the reaction mechanism for the reaction of carbonic compounds with metal and alcohol. So in the absence of proton donor, in the absence of alcohol, they undergo dimerization. Okay, so we'll see this one also. So in the absence of proton donor, okay, that is in the absence of alcohol, in the absence of alcohol, then dimerization takes place. Dimerization takes place. So for example, let's say, so I'll take one example. Okay, so let's say this alcohol, that one, okay, alpha, this one, sodium or metal, let's say metal, general reactions, metal. Okay, so metal gives a transfer electrons here. So first one is formation of this one, RCO negative and radical, okay, alpha. Okay, so you got this one. Use two molecules, so dimerization takes place without any proton donor. Then it comes to two molecules will come, dimerization takes place. Alpha, so here O negative charge. Okay, here then another one O negative, R prime, R. Okay, so we got the first one, the anion is formed. So dimerization, two of this molecule combined together, the radicals combined together, this one. Then this one followed by hydrolysis with the acid hydrolysis in presence of acid CiCl. So it gives the pinacol, or you can say 1,2-diols are obtained. Okay. So got that. Say 1,2-diols or pinacol. Pinacol or 1,2-diols. So in absence of proton donor, dimerization takes place, which can undergo acid hydrolysis to give the pinacol or 1,2-diols. So I will give one example. So here metals can be used in the form of metals. Metals used maybe say magnesium in the form of amalgam or sodium amalgam. Even zinc also, and even zinc amalgam was used. So amalgamated metals are used here. So in this case, reduction of metal in the absence of proton donor undergo dimerization, and after hydrolysis they will give 1,2-diol. So I will give one examples of this from this dimerization, okay, of ketones to give 1,2-diols. So let's say this benzophenol, okay, benzophenol in presence of sodium, or you can say magnesium amalgam. Let's say magnesium amalgam, okay. So let's say two molecules of benzophenol. So first we'll give like this. So attack here, we'll give the anion radical first. Formation of anion radical, O negative. Oh, there's a phenyl here. O negative here, the phenyl. Okay. So this will give 2 will come, okay. So magnesium here and 2 plus, okay. So 2 of this will give, so you have anion radical fast form and fast form this, okay. Then this can be written as like this. Dimerization takes place without any proton absence of proton donor, without proton donor, in absence of alcohol. So you can have phenyl here, so O. Then this dimerization takes place, O negative charge, and phenyl, okay. So here magnesium's liquid magnesium 2 plus, so we got a complex like this stem. So this without any in absence of proton donor, they go under dimerization. Then this acid hydrolysis with the presence of HCl or acid. So dimerization takes place to get this 1,2-diol, or you can say pinacol, okay, pinacol or 1,2-diol. So you got this one. So after hydrolysis, so what I want to say, in absence of proton donor, these compounds can undergo dimerization, and on acid hydrolysis of the dimerization, the product will give the pinacol 1,2-diols. So reduction with metal and alcohol can also undergo with not only with carbonic compounds, with ester also can undergo reductions. Esters can also be reduced. Can also be reduced to alcohol, primary alcohol. This is the primary alcohol by metal, and in presence of proton donor, there is alcohol, okay. So the alcohol ester can be reduced by metal and alcohol. This reduction of metal and alcohol can take place with ester also. Say for example, I give general examples. CO2 compared to with say metal in alcohol, it is to primary alcohol, okay, primary alcohol. Actually, this reaction take place like this. First step is formation of aldehydes. This can further reduce to primary alcohol, metal, and then proton donor alcohol, metal, alcohol, okay. So first step is usually form aldehydes are formed, and aldehydes are further reduced to primary alcohol. So in any way, Esters can be reduced by metal and alcohol to give this primary alcohol. So I will give some examples. Okay, one example I will give here. So I one example, many examples here also, many examples are here, but I will give one example here, many examples here, but I'll give one example, okay, simple one for reduction of esters to CN, C6 certain, or you can just see any compound ester CO, OET, okay, cyclohexyl esters, just to in presence of sodium metals in ethanol and xylene reflux. Okay, so here followed by first one, and then followed by hydrolysis in acid hydrolysis in presence of HCl. So acid hydrolysis will give, so this will give and C6H13 CH2OS alcohol. Okay, so these are all the esters can be also reduced like carbonic compounds to alcohols. So in absence of the proton donor, then they can undergo dimerization like carbonic compounds. So I will give some examples. Okay, so in absence of proton donor, they undergo dimerization, say like R, CO, OET. So first, in absence of proton donor, so you select ether or xylene. Ether, you can write E2, T2O, and xylene reflux. So first, this will give undergo dimerization to get one to diketone, and then the hydrolysis. First, we'll get this diketone COR, and then final hydrolysis with acid hydrolysis. This will give acid hydrolysis will give the acetylene to 1,2 ketone. You can say RCO, CHOS, R. Okay, so this is called acetylene, or you can say the alpha position alpha ketol, KOL ketol. Okay, alpha ketone, in the alpha position, alcohol is there, OL is there, so you call alpha ketones. So esters, in absence of proton donor, they undergo dimerization, and then after hydrolysis to give the acetylene. So as esters, I write down here, esters in absence of proton donor undergo dimerization like earlier cases for carbonic gases. In the case of carbonic compounds, dimerization to give the dimer, which on hydrolysis, acid hydrolysis yield this alpha ketone known as acetylene, also known as acetylene. Okay, so ester in absence of proton donor undergo dimerization, which on acid hydrolysis give alpha ketone acetylene. So this process is known as acetylene condensation. Okay, condensation. This process, formation of acetylene from esters in absence of proton donor, reaction with metal is known as acetylene condensation. So here also many reactions are here. So I will give the mechanism of the reactions. Okay, mechanism of the acetylene condensation. So let's see the mechanism of the acetylene condensation first. Okay, you have ester. Okay, general ester, OET. So first, in presence of sodium, ether. Okay, then just reflux heating first will give this attack here, this one attack, analytical form, CONA, this charge OET, so here Na will be positive charge. First step is formation of analytical form. So this, we use 2 molecules of this one, let's say 2 of this use, then undergo dimerization takes place. So you get R, CO negative, sodium plus, okay, OET. So here two of this molecule will come dimerization. So you get RONA. Okay. So now this coming back, the negative charge coming back, OET lost. So here the same case coming back. This negative charge coming back, and then with the gold. So you got it. First you got it diketon. Okay, so we got this one, 2 diketones are obtained. This again further gold reduction with metal 2 sodium. So first one go this way like this, other one this go like this. Okay, so we got, and as earlier like analytical or NA like this. Okay, so we got this type. This undergo, this two will dimerize. This will undergo this combining together to give a double bond here. So I'll write here. Okay, so we got first, we got a, this one will give now double bond here. So you give O negative charge, O negative charge. So like this. That's it. Now finally these are acid hydrolysis with water in presence of acid. So you got this R C double O C H O H R prime. Okay, usually like take this like this and gives this a proton donor. So you got a proton here, then this also pick up the proton, so it always comes like this. So this is the alpha ketol, or you can say epsilon. So this is the mechanism for how epsilon is formed. So reaction takes place metal in absence of alcohol or proton donor. Okay, so we got a epsilon many. So epsilon can, this epsilon can be used for many reactions for synthetic applications. So coming, so one of the synthetic applications of epsilon condensation is, one of the synthetic applications of epsilon condensation is ring formation, or you can say ring annihilation reaction. Annihilation of ring. So this type can be undergo by with these reactions with undergo with dicarboxylic esters. You can say diesters. Simply you can say diesters, and this is to condensation of ring formation takes place. So this is known as intramolecular epsilon condensation. Okay, epsilon condensation. So ring is formed. So mostly generally diesters are undergo ring formation in absence of proton donor. So I'll give you one examples. Okay, CO280, CH2, SA8, another CO280. So these diesters in presence of say sodium, first one sodium xylene in absence of proton donor, then followed by acid hydrolysis, diacetic acid, diacetic acid. So we'll give this undergo epsilon forms CHOH. So here CH2 8 like this. Okay, and CH2 8. So it has this ring is formed, a big ring form here. So it is called intramolecular epsilon condensations. Another implication is that for this one type of reactions can take place in steroid system also. Extension of ring can take place in the steroid systems. Another application of epsilon condensation is in the steroid systems. So here another extension of ring can take place. So I'll give one example. I'll give another example here. So let's say this is the OCH3 here, and then okay, this here CH2OH, or you can write here also, you can write CO2, or here CO2, or here CH2 CO2, so the esters are here. So this reaction with sodium in presence of in solution, okay, in solution, so in liquid ammonia, metal in solution, no proton donor here, then you can have second one is acid hydrolysis. So we come using intramolecular silent condition takes place here. So another ring will come here. So the product will be steroid, and steroid here. Prime member ring will come. Okay, so here OCH3 here. So here 1, 2, 3, 4, 5. So in this way, so you can get the carbon group here and the OH here, epsilon type, okay, alpha ketol. So like this. So here ring extension of ring takes place. One is another application of silent condition, intramolecular silent condition takes place. So ring formation takes place. So I have given another example here. Another example is here. Let's say this is R here, okay, some other R here. This is a cholesterol C7H13. You can write another cholesterol tag C8H17, okay. So here you can have CH2, CO2, diesters. And another here CH2, CO2, diesters, okay. So here same case, first one in presence of sodium and liquid ether, diethyl ether, then acid hydrolysis. So we'll get this one. So here ring formation takes place. So you can get here, okay, the steroid system. So here R is C8H17, okay, like cholesterol is cholesterol type ring, okay, extension. So here you can get this one here. You can have number 1 O here or O is here, okay. So extension take 6 member ring, 1, 2, 3, 4, 5, 6. So you can have 6 member ring here. Another product when here also check only the position of the carbon group. Then carbon group is different, okay. Here R here, R is can be this one C8H17, okay, like cholesterol, this one. So here also number 1 here, okay, the carbon group here, always here. So here position of the carbonyl or hydroxyl group is different. So you got alpha ketol, here also alpha, here also alpha, okay, alpha ketols are there. So the another applications of silent condition. So here intramolecular silent condition takes place. So the yield of this intramolecular silent condition can be improved. This yield can be improved by using the reactions with trimethyl chloride, okay, or chlorotrimethylsilane. So better yields can be obtained. Better yields of this type of reduction. This type of reduction can be improved. By using, you can say trimethyl silyl chloride, or you can say chlorotrimethylsilane. Okay, same case, chlorotrimethylsilane. This is the compound, okay, trimethyl silyl chloride, okay, or you can say chlorotrimethylsilane. So this type of this silent condition can be improved by using this silyl chloride. So I can give one example, say CO80, like let's say CH2, and this here, let's say 5 CO, so diester, okay. Diesters, in absence of proton donor, sodium toluene, then trimethyl silyl chloride, okay. So first cyclization will take place. So you get this sodium bonding 5, 6, 7, okay. You will get sodium bonding 2, 3. So 1, 2. So like the 1, 2, 3, 4, 5, 6, 7. 7 bonding will get. So here you get OSI. So CH3 trimethyl silyl, okay. So first what I get this one. What is sodium bonding? Then this acid hydrolysis with water. Acid hydrolysis water in presence of acid HCl, okay. HCl hydrolysis, this will give sodium bonding this is carbon group and CSOS, okay. Alpha ketol, cyclic alpha ketol in cyclic system. So nearly 75% takes place. So this is one example. So you can give another example also. You can have another example. We can have this one. I'll give this one intramolecular silent condensation. This compound is this is diester CO1 CO2 So in presence of sodium in toluene, and this trimethyl silyl chloride. So first formation of this to be cyclized, okay. So you get C double bond here, or let's say or it was step by step. Let's say first step will be without this, okay. First step by step. So ONA. So you know this thing mechanism first. So then we'll take here, then in a radical form, and this one, then here also in a radical form, then these two will combine. So I'll give the mechanism like this. First step is formation of this, okay, or C, okay, ONA, OT will form, okay, this or this let's say OT, yeah, OT, yeah. So first, then combine this together. You get COET, and this combine these two radicals combine, so you get OET. Then here O negative charge, and this will combine. Then OET will go. So you got a diketon first, fast. So this same mechanism we have, and this with two molecular of 2 atoms of sodium atoms will get ONA, okay. So this mechanism how it forms, this is the way. So this compound, let us say A, this can be react with trimethyl silyl. So I'll remove this one, okay. This A, so react with trimethyl silyl chloride. So you get oil here, C O S I Me3, so gas C O S I Me3. Okay, so you got this one. So you got this product. Then this for hydrolysis with acid hydrolysis. acetylysis in TSF trihydrofuran. So this will give O CIS voice acetylene. So another example, this one. So why I'm getting that these are another applications of for acetylene condensation. This can be improved by using trimethyl chloride. Okay. So we have discussed so far all this the reaction with metal and alcohol. I will just summarize today's lectures. So what we have done is reaction with metal and alcohol can be used for the reaction of carbon compounds to the corresponding alcohols. Okay, say aldehydes will give primary alcohols and ketones will give secondary alcohols. So in presence of methane and alcohol, carbon compounds are reduced to the corresponding alcohols. Then in absence of proton donor to alcohol, then dimerization takes place. Carbon compounds will give dimer phosphate in the presence of proton donor, followed by hydrolysis will give alcohol, you can say 1,2-diols. So 1,2-diols are obtained from ketones by reaction with metal in the presence of proton donor, followed by hydrolysis. Then similarly, reduction with metal and alcohol can be also applied to esters. When esters are react with metal and alcohol, they undergo reduction to give primary alcohols. Okay. So actual production is 2 aldehydes. Okay, 2 aldehydes. So same mechanism followed. So in absence of proton donor, these esters can undergo dimerization followed by hydrolysis to give acetylene. You can say alpha ketol. So this process is known as acetylene condensation. Acetylene condensation is a reaction of esters in absence of proton donor with metal followed by hydrolysis to give alpha ketol. So this acetylene condensation can be used for many applications. First application is with steroids, and then ring formation, ring annihilation, known as intramolecular acetylene condensation. Then you can apply to steroids, and then you can use trimethyl chloride for to get more yield. So this is about today's lecture. So next we'll take up reduction with lithium hydride or the hydride reaction. Okay, that is all now for this today.